a consensus that if a ninth planet does exist, it's not the one that scientists of the 20th century expected. But does this mean the end for any hopes of discovering another planet out there? Not quite. Just because there is no longer any evidence pointing to a giant planet close enough to alter the orbits of Neptune and Uranus doesn't mean that there isn't another planet further out. Like we said before, Neptune is so far away that we don't have the technology yet to get a clear picture of it. So it's not beyond the imagination that a planet could exist beyond it with an orbit so vast that we haven't managed to track it down yet. And there is still evidence to support this idea. Sedna, a TNO that was discovered in 2003. Its orbit is incredibly erratic and cannot be explained by any gravitational body we've observed thus far. While some theories proposed are that its orbit has been affected by the gravitational pull of an undiscovered star, other theories propose that the gravitational pull of a distant giant planet could explain it too. However, while Mike Brown, the astronomer who discovered Sedna, has stated that the balance of probabilities lies with there being another planet beyond Neptune, that it's unlikely the planet would achieve anything beyond dwarf planet status due to the amount of uncleared planetoids and gravitational objects in its vicinity. Is there a Planet X out there? While the jury is still out on what exactly is out there, we can say for certain that with the advancements we've been making in technology and with the determination of astronomers worldwide, someday we'll find out. The New Horizons probe that flew by Pluto in 2015 didn't detect any large unknown planets on its journey, but it did capture the surface and secrets of Pluto like we've never seen before. Click here to see exactly what New Horizons discovered on the surface of Pluto. Thanks for watching, Elder Fox. Remember to subscribe and hit the bell to keep up to date with the latest discoveries.
If he had to start there now, he would never get here. And the question of how far he walked is ambiguous. We could say he walked 99 meters because that was the distance at the beginning, or we could say that he walked 9,900 meters because that was the distance at the end, or we could say 460 meters because that is his normal speed times the time it took. The expanding universe exhibits the same characteristics. Light from the edges of the 42 million light year sphere began their journey to the spot where the Earth will develop about 13.7 billion years ago. But during the trip, the intervening space multiplied itself 1,090 times. And now the spherical shell from which the light began is about 46 billion light years away. This is the farthest into space we can see right now, and it is called our particle horizon. 100 million years after inflation, the first stars formed. They were massive giants that formed in every region of space, including our little sphere of observable universe. Those that formed on a shell a little inside our expanding particle horizon are just visible today. The light from these primitive giants has been traveling over 13 billion years. And the shell of space where they formed is now over 36 billion light years away. So light from the microwave background was emitted from a distance of just 41 million light years away. And that distance is now 46 billion light years. And light from the earliest stars was emitted from a distance of 1.5 billion light years. and that has grown to 36 billion light years. Due to the faster than light expansion of space in those early years, the light was actually moving away from us for billions of years before the slowing expansion allowed it to start moving towards us. Light we see today from some distant galaxies that was emitted from 5 to 6 billion light years away comes from objects that were the most distant at the time the light was emitted. Massive objects like the Earth and the Sun, that are gravitationally bound to one another, can overcome the expansion of space between them. Space is expanding in our system, but the distance from the Earth to the Sun does not change because of this expansion. Why? Because as space expands, the Earth's orbit continually adjusts to keep the Earth at the correct distance that is demanded by the law of gravity. This is also true for stars inside a galaxy that are gravitationally bound, and is true even for local clusters of galaxies. As space expands, the distance between the bodies constantly adjusts to comply with the laws of gravity. The wavelength of light from distant objects is shifted toward the red end of the spectrum if they were moving away from us. And the expansion of space is measurable by measuring the redshift. And unlike the Doppler redshift, the cosmological redshift says nothing about the recessional velocity of the emitting object, either at the time the light was emitted or at the time the light was received. Hubble's law says the further away an object is, the faster it is receding without limit. So, there are always objects far enough away to be receding faster than the speed of light. Objects we see with a redshift of about 1.46 are moving away from us at the speed of light, and all objects with larger redshifts are receding faster than the speed of light. Most objects in the extended universe are traveling away from us with velocities fast enough that we will never see them. In effect, we have an event horizon. And events beyond our event horizon are effectively unknowable to us. Objects that have a current redshift of about 1.8 are currently about 18 billion light years away and are now crossing our event horizon, never to be heard from again. Finally, this is a time sequence of the evolution of our universe. Big Bang, followed by inflation, reheating or the birth of matter, birth and death of the first stars, and the ongoing formation and growth of galaxies. When we look out into the universe, we're looking backward time, looking at the universe as it was when it was a lot smaller and a lot younger.
All across the immense reaches of time and space, energy is being exchanged, transferred, released in a great cosmic pinball game we call our universe. How does energy stitch the cosmos together? And how do we fit within it? We now climb the power scales of the universe. universe. From atoms, nearly frozen to stillness, to Earth's largest explosions. From stars colliding, exploding, to distant realms so strange and violent, they challenge our imaginations. Where will we find the most powerful objects in the universe? Today, energy is very much on our minds as we search for ways to power our civilization and serve the needs of our citizens. But what is energy? Where does it come from? And where do we stand within the great power streams that shape time and space? Energy comes from a Greek word for activity or working. In physics, it's simply the property or the state of anything in our universe that allows it to do work. Whether it's thermal, kinetic, electromagnetic, chemical, or gravitational. The 19th century German scientist Hermann von Helmholtz found that all forms of energy are equivalent, that one form can be transformed into any other. The laws of physics say that in a closed system, such as our universe, energy is conserved. It may be converted, concentrated, or dissipated, but it's never lost. James Prescott Joule built an apparatus that demonstrated this principle. It had a weight that descended into water and caused a paddle to rotate. He showed that the gravitational energy lost by the weight is equivalent to heat gained by the water from friction with the paddle. That led to one of several basic energy yardsticks called a joule. It's the amount needed to lift an apple weighing 100 grams 1 meter against the pull of Earth's gravity.
Today, we're going to find out if AI can make me a better programmer. This video is sponsored by Tab9, which is a code completion tool powered by machine learning. We're going to put it to the test to see if I can become the ultimate programmer. We'll be doing 3 tests. Speed, where I'll type out a section of code using the code completion tool. Then I'll type out the same code without the code completion, and I'll time both to see what the difference is. Next, we'll test learning. I'm going to write out some code in a language I'm not very familiar with, and we'll see if Tab9 can help make that process a little smoother using suggestions. Last, since Tab9 uses GPT-2 for natural language processing, I'm going to test if it can help me write out comments to my code. To give an idea of how machine learning and AI can power code completion, Tab9 is trained on both GPT-2 for natural language processing, as well as Common Code Semantics from credible open source projects. Tab9 is free and works on a number of IDEs for most modern programming languages. You can install it from the website in the description below, or you can go to your IDE, search for it in the extensions tab, and download it there. Let's begin the tests. In this first test, I typed out a script that I recently wrote for Strain. It changes the textures of a building at random intervals throughout the evening to make it appear like lights are turning on, and vice versa, turning lights off in the morning. By the way, this is definitely my regular typing speed. It's not sped up at all, definitely not. In this first run through, I'm not using Tab9 to assist. It would be a lot slower if I were typing this out for the first time instead of referencing a script I already wrote, but it would have been more difficult to compare the 2 runs with a fresh script. I ended up writing it in just under 7 minutes. In the second run, I'm using Tab9 to assist the coding by autocompletion. You can see in some areas it writes out entire lines of code, which is really cool. This is more helpful when you're actually writing the code for the first time because you're just looking in one place. It sometimes fills in that brain lag that comes up when you're thinking of what to write next. I also find it helps me remember variable names when I forget, since it offers a suggestion for that as well. This one went a lot quicker, wrapping up at 5 minutes and 37 seconds. So for the next test, I'd like to see how a Tab9 can help me learn a new language. In this case, I'm going to try to use some PHP, which I suppose isn't a new language, but it's one I haven't used in a very
Remarkably, they are still not the most powerful events known. Albert Einstein's equations contained an astonishing prediction that when massive bodies accelerate or whip around each other, they can stir up the normally smooth fabric of space-time. They produce a series of waves that move outward, like ripples on a pond. Scientists are now hoping to detect these gravitational waves and verify Einstein's prediction using precision lasers and some of the most perfect large-scale vacuums ever created. At the Laser Interferometry Gravitational Wave Observatory, known as LIGO, they are hoping to record the collision of ultra-dense remnants of dead stars known as neutron stars and of black holes. According to computer simulations, as two black holes spiral into a fateful embrace, the energy carried by each gravity wave rises 5 orders of magnitude above a gamma ray burst to 100 billion trillion times the power of our sun. Does the collision of black holes define the known power limits of our universe? Perhaps not. As turbulent as the environment of a black hole might be, its true power may well lie deep in its core. A black hole's mass is enshrouded within a dark sphere called the event horizon. Since the 1920s, scientists have described the mathematics of the event horizon as the equivalent of a waterfall.
Make you feel anxious?
Of a waterfall. It's the point of no return, beyond which water falls freely. It's the point of no return, beyond which water falls freely into the gorge. At the event horizon of a black hole, space itself at the event horizon of the speed of light. Space itself falls freely in at the speed of light. If the black hole is spinning, then the flow spirals down and around. If the black hole is spinning, that envelops, then the flow spirals down and around an inner horizon that envelops the singularity. That's the central region where space-time becomes infinitely warped. That's the central region where space-time becomes infinitely warped. Any matter that rides this river of space whips around the inner horizon so fast. This river of space force whips around the inner horizon so fast that centrifugal force tends to fling it back out. As that happens, it collides with matter that's streaming in. As that happens, it collides with matter that's streaming in, whipping up a ferocious cosmic storm. The energy of the colliding stream feeds upon itself, rising. The energy of the colliding stream feeds upon itself, rising to what may well be a limit imposed by nature. It dissipates only as it falls into the singularity and disappears. It dissipates only as it falls into the singularity and disappears. Fortunately for us, gravity walls off such energy extremes behind the event horizon. Gravity walls off such energy extremes behind the event horizon, where they cannot affect the rest of the universe. And so here we sit. Our world is nestled within a vast stream of cosmic energy. Our world is nestled within a vast stream of cosmic electron. And the maelstrom of the black hole. An electron. And the maelstrom of a black hole. There's no telling whether a future Earth civilization will be able to harness enough energy to advance into the cosmos. Will be able to harness enough energy to advance into the cosmos. For now, as we tap into the tiny morsels of power at our disposal, as we tap into the tiny morsels of power at our disposal, at a universe blazing with activity. We venture a closer look at a universe blazing with activity. We are its product. We are its product. And it's starstruck admirer. And it's starstruck admirer.
4.6 billion years ago, our sun started to form 4.6 billion years ago out on one of the spiral Our sun started to form about 2/3 of the way out on one of the spiral third generation star. Starting from gaseous clouds and third generation star, containing many heavy starting from gaseous clouds and dense nebulae, it condensed under the immeasurable pressure of gravity until it was hot and dense enough. It condensed under the immeasurable pressure of gravity until it was hot and dense enough to experience nuclear fusion. Our sun is an average yellow star. As stars go, but it is so massive that it contains 99.8%. But it is so massive that it contains 99.8% its radiant energy supports almost all life on Earth, and its radiant energy supports almost all life on Earth. And it is almost 900,000 miles in diameter. It is almost 900,000 miles in diameter, 15 million degrees. It has a core temperature of about 6,000 degrees. And its surface temperature will be fairly stable over the next 5 billion years. The sun will be fairly stable over the next 5 billion years. At which time it will expand its red giant so that its outer layers will reach the current orbit. It will expand enormously, so that giving it a diameter of almost 200 million miles. Giving it a diameter of almost 200 million years as a white dwarf. After that, it will live a few billion more years as a white dwarf. Mercury is the smallest planet in our solar system. It is only about 3,000 miles in diameter and has a surface that is about 3,000 miles in diameter and has a surface that is the innermost planet and has an elliptical orbit that takes it within 28 million miles of the sun and has an elliptical orbit that takes it within 28 million miles of the sun at its 43 million miles at its most distant. And out to 43 million miles, it takes Mercury 88 days to orbit the sun. It takes Mercury 88 days to orbit the sun. Although it rotates once every 59 days. Although the day on Mercury is every 59 days, Earth days long. The day on Mercury is 176
will be
Earth days
needed,
long.
he says, after the 19th of July. Numbers are getting bigger again, more positive tests and the like. There's talk, serious talk, of vaccinating children against COVID-19. People under the age of 18, the EU are certainly keen. 19th of July is the latest in a long line of dates dangled in front of us pros and called something like freedom.
Venus is the brightest object in the sky, except for the sun and the moon. And since it is closer to the sun than we are in the sky, it shows phases. And since it is closer to the sun than we are, shrouded in permanent clouds like the moon. Venus rotates on its axis shrouded in permanent clouds 3 days. Venus rotates on its axis backwards from the other planets 3 days. And it is only slightly smaller than the Earth. And it orbits the sun every 225 days. And it orbits the sun every 67.5 days. At a mean distance, but its surface is terribly inhospitable. The atmospheric pressure at the surface is 92 times that of the atmospheric pressure at the surface is 92 times that of the Earth. Similar to the pressure, its temperature is a balmy 900 degrees Fahrenheit. Its temperature is all in all 900 degrees not Fahrenheit. A good vacation spot. All in all, not a good vacation spot. Our Earth is 8,000 miles in diameter and rotates on its 8,000 miles in sunrise every day and rotates on its axis, causing sunrise every day. It is the largest of all the planets that have a solid surface. And it is the largest and unusually large moon that have a solid planet of its size. And it possesses an unusually large moon since the moon circles the Earth. We think of the moon's motion as circular. Since the moon circles the Earth, but since the Earth we think of its motion revolves around the sun at about 65,000 miles per hour, revolves around the sun at about 65 solar systems isn't much different from our own. The moon's motion in the solar system isn't 93 million miles from the sun. The Earth is the third innermost planet, 93 million miles from the sun, and is the only place in the solar system that we know of that has and is the only place in the solar system that we know of that has liquid water. Mars is the planet most similar to Earth in terms of habitat. Mars is the planet most similar to Earth in terms of habitat. Although smaller than Earth and Venus, it has a thin atmosphere. Although smaller than Earth and Venus, it has a thin atmosphere. And probably had liquid water on its surface and has prompted us to send a plethora of probes. This attracts our interest and has prompted us to orbiting irregular-shaped rocks, graciously called moons. It has two orbiting irregular-shaped rocks, graciously called moons, which are probably captured last about 24 hours. Very comparable to our on Mars lasts about 24 hours. The volcano called Olympus Mons, or Mount Olympus, the volcano called the highest mountain in the solar system. Mount Olympus. It is the highest known mountain in the solar system and is over 3 times the height. It is an extinct volcano and is over 3 times the height of Mount Everest. Mars is the fourth planet from the Sun and completes its orbit. Mars is the fourth planet from the Sun and completes its orbit every 2 Earth years. Jupiter is huge. If it had only been a little larger, it could have become a brown dwarf star. If it had only been a little larger, it could have become a gas dwarf star circling our sun. It is a gas giant and has bands of poisonous clouds that circle the planet. Its atmosphere forms bands of poisonous clouds that circle the planet in opposite direction. The giant red spot is a huge storm that has been raging for hundreds of years. The giant red spot is a huge storm that has been raging for hundreds of years. Are so large that Galileo spotted them. 4 of its many moons are so large that Galileo spotted them with his primitive telescope in 1610. All of the gas giants have rings. In addition to moons, but Jupiter's rings are so faint they are not visible. But Jupiter's rings are so faint they are not visible. The fifth planet out, Jupiter orbits the Sun at a distance of 480 million miles. Jupiter orbits the Sun and takes almost 12 years, 80 million complete circuit, and takes almost 12 years for one complete circuit. Notice the large separation between the orbits of Jupiter and Mars. Notice the large separation between the orbits of Jupiter and Mars. It is the debris. This is the realm of the asteroid form. Because of Jupiter's, it is the debris of a planet that failed to form because of Jupiter's gravitational influence.
Giant boulders awkwardly teetering on top of one another.
Saturn is the second largest of the planets. Only Jupiter is larger. Is the second largest of the planets. Like all the gas giants, Jupiter it has a system of rings. Like the rings of gas giants, it has a system of rings. And the rings of Saturn, Saturn also has dozens of moons. And one of them is particularly notable. Also has dozens of moons. And one of them is the second largest moon in the solar system. And it possesses an atmosphere for the second largest moon in the solar system. And it possesses an atmosphere. It is primarily composed of water, ice, and rocky material. It is primarily composed of water, ice, under the clouds, and rocky and surface ice. It is even Titan has liquid under the clouds and surface and maybe even microbial life. Titan has liquid water, and maybe it is even 50% larger in diameter than our own moon, and it is 50% larger in diameter than our own moon, and 80% more massive. Saturn takes 29 years to orbit the Sun, and does so at a distance 29 years to orbit the Sun, million miles, and does so at a distance of 890 million miles. Uranus rolls on its side. It is an icy giant of a planet. Uranus rolls on its side, the third largest in the system. It is an icy giant like the other giants. Uranus has a largest in the system and numerous moons. Like the other giants, Uranus has a seventh planet and numerous moons. And it orbits the Sun at a distance of 1.9 billion miles. And it orbits the Sun at a distance of 1.9 billion Earth years. A year on Uranus, because of its extreme axial tilt. Seasons on Uranus, because of its extreme axial tilt. At the time near the solstice are worth one pole continually faces the Sun. At the time near the solstice, the other faces away. One pole continually faces the Sun. Strip near the equator, while the other faces away. Experiences Uranus a narrow strip near the equator. experiences at the other side of Uranus's 17-hour day. The orientation of the poles at the other side of Uranus's orbit, so each pole gets 42 orientation years of the poles continuous day. So each pole gets 42 years of continuous day, followed by a 42-year night. Let's head to a point high over the ecliptic, so we can see the relative sizes of the orbits of the sunward planets. So we can see the relative sizes of the orbits of the sunward planets. Neptune is a blue world. It is the smallest of the giant planets in our system, but it is the smallest of the giant planets in our system, but still 30,000 miles in diameter. Since the demotion of Pluto, it is the furthest planet from the Sun. Since the demotion of Pluto, Neptune's rings are very faint from the Sun. And of its 13 moons, Neptune's only Triton is massive enough to be round. And of its 13 moons, only Triton is massive every 16 hours and orbits the Sun every 116 hours and orbits the Sun every 185 years at a distance of 2.8 billion miles. Pluto is now deemed a dwarf planet and a member of the Kuiper Belt. Pluto is now deemed a dwarf planet and a member of the Kuiper Belt is a region of the solar system. The Kuiper Belt is a region of the solar system that extends just beyond the orbit of Neptune, at about 2.8 billion miles out to about 5 billion miles. Like the asteroid belt, it is crammed with many small bodies orbiting the Sun, most of which are frozen methane, ammonia, and water. Here's a size comparison. Earth.
The going is tough
Ganymede,
through a dense jungle of mango, wild
Titan,
banana, and palm,
our moon.
and the expedition makes slow progress, trailing machete-wielding guides. The year is 1860, and these remote forests have never before been seen by Western eyes. And what wonders there are. Plants, trees, and animals completely unknown in Africa, just a few hundred kilometers to the west, let alone the rest of the world. Bloated baobabs, delicate orchids, and above all else, lemurs. As the exhausted party rest within the sweltering understory, a family of these curious animals clatters noisily through the canopy overhead, shrieking their alarm at the intruders below. Dense foliage hides the mammals from view, but a rare glimpse shows a long, black and white striped tail swung out for balance. Below, one of the Westerners wipes sweat from his brow as he hastily notes down the sighting. Another novel variety to add to his ever-growing list. By the end of that year, that wonder-struck adventurer had survived the voyage back to England. Presenting his sweat-stained notebook, along with several crates of samples, to the secretary at the Zoological Society, Philip Slater. Slater had made a name for himself in the realms of ornithology, proposing a new way to divide the globe, based on the distributions of birds. But, as with many of his fellow scholars of the Victorian age, his curiosity about the natural world could not be contained. And now he turned his attentions to the mammals of Madagascar. He pored over the specimens returned to him, probing and classifying with intense fervor. And slowly and surely, a seed of an idea grew inside his mind. There was indeed a staggering bounty of lemur species in Madagascar. Ring-tailed lemurs, like the one glimpsed through the trees, were joined by 29 other distinct types. Such variety for such an isolated island. In comparison, Africa boasted a mere 12 species, and the Indian subcontinent only 3. The implication could not have been clearer in Slater's mind. Madagascar had to be the primordial homeland of these tree-dwelling mammals, from which the Asian and African varieties were derived. But how had they crossed the great oceans between? Slater was once again confident in his conclusion. They must have travelled overland, across a land bridge that had once connected Asia, Madagascar, and Africa. Such a bridge must have been gigantic in extent, occupying much of the western Indian Ocean. In fact, it would be more fitting to call it a continent. Slater named this hypothetical lost continent, the supposed connection that allowed lemurs to flow out of their homeland, Lemuria. At this point of the 19th century, the idea of lost continents was not such an outrageous one. As geologists strove to understand the rocks that painted the globe, they imagined ocean basins as sunken, drowned landmasses. Our continents today may have been raised, dripping from the seabed, producing marine fossils in unlikely inland locations. So, Slater's proposition of the sunken continent of Lemuria was a sensible, scientific supposition. Following decades would see his ideas seized and transported outside the realms of science, and ultimately into the occult. In 1876, a new rejection of the theory of evolution was published by German zoologist Ernst Haeckel. His History of Creation not only rejected Darwin's suggestion that humans had evolved and radiated from Africa, preferring an Asian origin instead, but suggested it was Lemuria that the lost cradle of humanity could be found. For Haeckel, it was here, among the lemurs and other lower primates, that mankind first emerged, spreading to Asia and Africa before the continents sank. In later translations of Haeckel's work, maps depicting Lemuria in the Indian Ocean were labelled Paradise. In the decades that followed, the idea was transformed yet further. For the Russian medium Elena Blavatsky, whose esoteric religious doctrine, Theosophy, was followed by 45,000 at its peak, including members of high society, Lemuria was the mythical homeland of one of the 7 races of humanity. A group of egg-laying hermaphrodites endowed with 4 arms and 4 eyes, who lived alongside dinosaurs on the lost continent until its fiery destructive end. The concept of Lemuria, from its well-intentioned scientific beginnings to its strange transcendence into the occult, was one that nevertheless persisted well into the 20th century. It wasn't until modern theories of plate tectonics came to the fore that the lost continent was finally sunk. And so, the last 60 years of geological and geophysical study have revealed an altogether more provable history of continental movements through time. Rather than merely rising or sinking, they traverse the globe, joining and splitting, building and shattering. Lemuria may never have existed, but we now glimpse an even more evocative past. There are generations of Earth's long-lost supercontinents waiting to be discovered. This video is sponsored by Magellan TV, the documentary streaming service. Magellan have been great supporters of the channel for a while now. They offer a vast range of programs on a truly comprehensive range of topics, more than 3,000 in total. From the depths of space to the dinosaurs, there's something here for everyone. Head over to History of the Universe to find out how they've inspired our work. And one Magellan doc that we enjoyed recently that pairs nicely with this video on supercontinents is Super Volcanoes, a fascinating exploration of what makes these Earth-shaping titans tick. And you can now take advantage of an exclusive offer, 30% off an annual membership. This gives you an entire year for less than $3.50 a month, even if you've joined Magellan before and lapsed. You can simply click on the link in the description to claim your discounted membership today. Towards the end of 1994, a small spacecraft plunged, whirling, into the scorching clouds of Venus. It was a graceful death, well deserved by a probe that had accomplished so much in its short life. For the last 4 years, the Magellan probe had been swooping past the shrouded planet in great polar loops, passing from north to south just 300 kilometers above the surface, before swinging far out back into space to prepare for another pass. With each transit, as the planet rotated serenely beneath its clouds, Magellan imaged a new swathe of the Venetian surface. But normal cameras would not suffice here. Earth's twisted neighbour is so thoroughly wrapped in cloud and haze that visible light could not hope to penetrate. Instead, Magellan scanned the alien surface with radar, and in less than 2 years had mapped 98% of the surface in unprecedented detail. But the radar images revealed something strange. Venus seemed to have no continents at all. Despite being so similar to Earth in size and rocky composition, the swaddled planet seemed to have none of our surface diversity. Magellan saw plenty of volcanic features, from shield volcanoes to vast lava fields, but they were all hallmarks of a single basaltic rock. No sedimentary deltas, no metamorphic mountains, no explosive stratovolcanoes. Only dark, fluid lava over the planet's entire surface. Magellan's data was invaluable to scientists trying to understand how Venus became Earth's evil twin. The radar images revealed that the plate tectonics that define our surface never really played a role on Venus. Without the lateral movement and recycling of the crust, there was nothing driving the creation of new types of rock. Without a tectonically driven rock cycle and being positioned that much closer to the Sun than Earth, Venus's conditions spiraled out of control. Without plate tectonics, the planet was baked alive. Earth was dealt a luckier hand. The beginning of plate tectonics established a feedback cycle that has protected us from Venus's fate for the last 3.5 billion years. Those plate tectonics have also endowed our planet with a startling variety of rock types, and we can trace the first continents of all to those earliest creeping moments. Continental crust is special. It has a distinct and refined composition, like a fine whiskey to the raw grain mash of the oceanic crust. As plates collide, they crumple and thicken, allowing molten. Here, they partially crystallize, losing their heavier minerals and becoming progressively lighter and less dense. It is these relatively lightweight granitic rocks that are the foundation of our continents. And they have been gradually accumulating ever since plate tectonics began. Because of their lower density, they float buoyantly on the top of the mantle and are not easily subducted at collisional plate boundaries. Instead, it is the denser basaltic, oceanic crust that floats lower and is sacrificed at